Next up, we have Adam telling us about index types for statically safe WebAssembly. I'll give you a 5 and a 2.
Sounds good. All right, hello everyone. This is work that I've done with my collaborators. You might recognize one of them. So WebAssembly, or Wasm, it's used in a lot of places, such as the cloud, Internet of Things, embedded systems, and beyond. And it's really great. It has a bunch of wonderful design goals, such as speed, safety, portability, and a small binary footprint. And that comes because it was originally designed for the web or browser context. Now, one thing about Wasm is it has dynamic checks on certain instructions. And so this is one on memory. Memory in Wasm is basically a linear region. Think of it as a giant array. So any access to memory within that array is good, but any other access is not good. And so the typical story for making this check be very quick and efficient is to just reserve a huge amount of virtual memory, deny access to everything outside of the region, and that way any check that's inside the region is good, and any check outside the region will just be caught by hardware, and the trap, which is the Wasm term for an error, will be propagated back up. Now, this uses a lot of virtual memory, which makes sense in the web or browser context, but in a lot of the other contexts, it doesn't make sense. I mean, we don't want to be reserving an entire 32-bit address space on an embedded system or a smart light bulb. So what happens when we don't have virtual memory? Well, this becomes expensive. And if we zoom out, the problem is that we have these dynamic checks to enforce safety. And most of the time, we can make these checks be efficient. But there are some contexts we care about where these aren't efficient anymore. And for those contexts, we want static safety. Now, a typical way to achieve static safety is a type system. So that's what we're going to introduce today. We're going to introduce Wasm-prechk, which shows how more expressive types can make Wasm statically safe. In a little bit more detail, this is a type system-based approach to reasoning about Wasm safety statically. There are several instructions in Wasm that include dynamic checks, including, as we saw, memory accesses, both load and store. Also, there are checks for things like division by 0. And then call indirect has which is basically kind of like a function pointer, has a runtime type check on the type of the function that winds up being called. We support all of these, but we're only going to talk about memory today because we find that to be the most interesting in practice. Now, the type system is responsible for ensuring that these new instructions that don't have dynamic checks are safe statically. And we find that when we're able to use the type system to justify removing these dynamic checks, we get a significant 1.71x speed up in memory-intensive benchmarks. So let's take a look at how dynamic checks work in Wasm, so we can kind of see how Wasm-prechk can go about helping us to safely get rid of them. So here's a program, and it's basically the Wasm style of a for loop. For those of you who know Wasm, maybe you'll understand what's happening here. For those of you who don't, hopefully you just trust me. So the first part is basically doing some pointer arithmetic on the array and the loop iteration variable to come up with the memory address that we're then going to load. We have the code that will load the loop iteration variable, add 1 to it, and then set it back, which will increment it. And finally, we have the code to get the local, check whether it's less than the size of the array, and if it is less than the size of the array, we continue the loop. And one thing I should say is that Wasm is a stack-based language, so all of these instructions are pushing values onto or consuming values from the stack. And we can see this in the simplified reduction rules for memory load. And in fact, you'll notice there are 2 of them. So we can see that this dynamic check is based into the semantics of the memory load rule. In one case, well, in both cases, we're going to consume a value k from the stack, and then we're going to look it up in memory. And we're going to see if there's a value at that location in memory. And if there is, then we push that onto the stack. And if not, we have a trap, which is a Wasm error. Now, what information does Wasm give us about these programs? This is the Wasm typing judgment, which says that under the context C, which gives us information about functions and other module-related items, the instruction sequence, the star operation is kind of like in regular expressions where it means 0 or more of something, and the E represents a Wasm instruction. So this is saying that there are some number of instructions, possibly 0, that have the type, and this is a stack type. So this on the left here is a precondition on the shape of the stack, where there are some number of t's on the stack before the instruction, and some number of t's on the stack after the instruction. These t's are either 32 or 64-bit integers or floating point numbers. So going back to our example, these first two instructions, I'm skipping a few steps here, but for the purpose of understanding, they both push 32-bit integers onto the stack, which is what we see here. We go from an empty stack to one with two 32-bit integers on it. Now we're going to add them together, so we're going to consume both of those 32-bit integers from the stack, and we're going to push a new 32-bit integer back onto the stack. Finally, we get to the load operation, and all we see is that there's a 32-bit integer on the stack before the operation. So if the size of memory is an entire 32-bit address space, this is safe. For any other size of memory, we don't know. Now, the Wasm-prechk type system is going to look similar to the Wasm type system, but it has a little bit more going on. So now, instead of these TIs on the stack before and after, instead of T's on the stack before and after, we have these TIs as well as P's on the stack before and after. We still have the same module type context and instruction sequence, but now the precondition and postcondition on the stack have extra information. This TI is a pair of a primitive Wasm type T. So again, we've seen that before. But we also now have this index variable x. And the index variable x basically lets us refer to the value in that position on the stack within the index type system. Because the index type system is basically a type system with an index language that allows us to express constraints over the index variables. So this is how we relate index variables to the program values that we then want to constrain. How do we constrain them? Well, that's what this P star is. It's a set of constraints, and they basically look like your kind of standard ways of constructing refinements. This is a little bit of a lie. The full details are in the paper. So going back to memory load, we still have the same memory load instruction in Wasm-prechk, and there's a dynamic check happening still. So we still just take some 32-bit integer, output some 32-bit integer. But now we introduce this new instruction, memory load precheck. And what that will do is it will take a 32-bit integer, and now we're going to represent the value by this index variable x. And now we have this constraint set, so we can have this side condition that the constraint set ensures that x will be within the boundaries of memory. And this gives us the static safety guarantee. So going back to the prior example, we're going to take that memory load and we're going to say, you know, I think this is safe. This doesn't need a dynamic check. So we're going to replace that memory load with a memory load precheck. Now we still have to do a bit more work, because we have to justify to the type system that this is actually safe. Because, again, unlike memory load precheck doesn't have a dynamic check based into the semantics. It has to succeed. So we start as before, and we have empty on the stack beforehand. Now we have two 32-bit integers on the stack after. Except now we have two index variables, x and y, associated with those values on the stack. And we have some constraints about them. X is equal to a, y is equal to I. And local variables can be mutable, so this is kind of a simplification of how we deal with local variables. The full details are in the paper. Now we're going to do this binary operation instruction, and we're going to consume x and y, and we're going to put a new 32-bit integer on the stack, z. And then we're going to add the constraint that z is equal to b plus c, which, in other words, we do some algebra, and z is equal to a plus I. So now we get to this memory load pre-check, and we take some z, and then we're going to return some w. But now we have this side condition that we need to show. And that is that given this z, is z less than the size of memory? And we don't know that based off of what's available to us at this point. We need a little bit more information. So the way we can provide that information to the type system is by adding annotations to blocks and functions. So here, because it's a for loop from I equals 0 to I is less than the size of a, then a straightforward loop invariant is that I is less than the size of the array. And all we have to do is write down this annotation, and Wasm-prechk will ensure that this holds for us. So now we have a little bit of information about I, but we still don't know anything about A. What we want to know is that the entirety of the array that A is representing is within the memory bounds. And the way we're going to do that is by adding a dynamic check. This dynamic check is not baked into the semantics. This is one we're just putting in there ourselves. And this is basically saying that the array from start to finish is within the memory region size, and otherwise there's a trap, Wasm error, which is raised by this instruction unreachable. And basically this says that there is only one path that will ever reach the loop, and that is the path in which the entirety of the array A is within the memory bounds. So now we can add that property to the loop annotation, and it all checks out, and now it's safe. So instead of checking this access every time through the loop, we're going to add this explicit check before the loop that only checks it once, and then we don't need the checks inside of the loop anymore. And this might be a simple thing, but it's actually quite powerful. In our benchmarks, this is a complicated graph, but lower is better. And look how low things go, yay. So the baseline we're comparing to is a version of Wasm where we just do every dynamic check in the expensive way. If that's the red dashed line at the top, everything else is relative to that. So this is our type system-based approach, and we see that in some cases we don't get very much speed up. In some cases we get a lot of speed up. Usually the longer running and more memory intensive benchmarks get more speed up. We also have a version of Wasm that just does no dynamic checks whatsoever, just YOLO it. And this is unsafe, of course, but it gives us a theoretical upper bound on performance. Finally, we have the virtual memory technique. And we see that in a few cases, specifically this Glam-Schmidt one, we see that it looks a little bit higher than the other two. And we're not sure whether this is due to experimental error or if there's some allocation cost to the virtual memory. So Wasm-prechk gets an average of a 1.71 speed up, which is 97% of the theoretical upper bound by the no checks whatsoever mode, which gets a 1.76 average speed up. And then the VM technique gets a 1.73 average speed up. So all of these do a much better job than the expensive dynamic checks, but we do it with Wasm-prechk without virtual memory. And we do it with a low overhead, so there's only an extra 7% average binary size. It's a little misleading because this is not just over the functions we're annotating, this is over the entire binary, which includes a bunch of libraries and stuff. So we find maximal utility when annotating a few more memory-intensive functions. And we find a very slight compilation overhead given that we now have to do constraint solving as part of a type system. Now, I did have to provide some information to the type system so that we could justify this, and preferably this wouldn't be the case. So we have a few ideas for how to get rid of that, including some sort of type inference or a static analysis. If you remember the example, then something like perhaps just a range analysis might do the job. Finally, you might preserve it through compilation through something more high level. So that's been Wasm-prechk. Thank you.
Thanks, Adam. That was fascinating. We're going to have so many more questions than we have time for. We're going to start with Neil, and then we're going to go to Discord after that.
Hi, thanks for a very nice talk. In your typing judgment for your Wasm-prechk, it looks like the assertions are only about stack variables. Have you thought about extending it to make assertions about the linear memory as well? So maybe you could prove that you're zeroing out an array or something?
So I'll say two things. The first thing is that we do include more assertions than just the stack. This is a simplification. Specifically, we keep track of local variables as well. We thought about that a little, but I think that would be very interesting to be able to kind of extend this work to tackling like a full-on memory allocator. So we've thought about it a little, but we haven't done much about it.
Thank you.
Thanks. I had a question that was in some way about utility of applying type systems to Wasm, especially in its intended use case of being kind of loaded as part of websites. Obviously, in some sense, we want to avoid bad actors potentially, sending code that will crash browsers or other unwanted behavior. Would you intend that this kind of typed extension become part of the thing that is transmitted and then checked in browser before running, or is this more for a different application domain?
Right. So theoretically, with more expressive types, you can check more richer properties. In terms of Wasm-prechk, we have standard metatheoretic proofs that it has the same level of safety as Wasm. We don't have anything beyond that necessarily. So potentially you could use it to check against a richer type and consider that for security. We've mostly been focusing on the performance aspect, though.
We are technically out of time. I just want to quickly check to see if our next talk, which is a virtual talk, is online as far as we know. I know that it's supposed to be online. I don't know if they're online. They are here? Great. Let's switch over to the stream. And while we're doing that, we'll take